All right, folks, I think this is pretty close to our last video for chapter 14. It's possible that I'll do like a homework help video. I was looking at the problem set. A couple of those problems I think I may have to kind of tweak a little bit. Okay, classic problems. So I'll certainly expect you to do this on a quiz or a test. Is you pick up a bottle of an acid or base solution. It has the chemical formula of something on it. It has the concentration of that. And I'd ask you to calculate the pH or the POH or all the other stuff. So this is an ice problem. This is an ice analysis applied to acids and bases. So the kind of problem here is if you're given a Ka or a Kb, find the equilibrium concentrations of all species, but these are acids and bases, so that's pretty straightforward. And then on top of that, just add in what we already know how to do, pH, POH, and then just for good measure, we'll reach back and do the percent ionization as well. I don't want to hammer these problems too hard, and I'm going to do these two side by side, because one's an acid and one's a base. How do you know? Well, there's a couple ways you could know. You could read the problem, and if it calls it acetic acid, okay. This is methylamine, which we used in the last lecture, so I gave you a Kb, so that's a base. So that sounded maybe a little simplistic, but if you have a table of Kas and Kbs, like from the appendix or a separate sheet of paper, just look up the chemical formula or the name, and if it lists a Kb, which it does for this, it's a base. If it lists a Ka, well, then it's an acid. So just you have to use a little bit of common sense to know what are you dealing with. So these get tricky because these problems all start to look the same. What's the pH of a such and such solution? Well, you want to know, is it an acid, is it a base? Does it have a Ka or a Kb? And then go from there. Once you do that, then you can start to set up these problems like we've always done. In fact, I'm going to set these up side by side if that's okay. So we know that this is an acid. And it's a weak acid because it has a Ka that's really small. We know it's a weak acid. It's not a strong acid where we would just take minus log of 1, and then for POH, minus log of 0.1. We know it's not strong, so we don't want to forget all that stuff. We know it's weak, so we actually have an equilibrium. So in this case, we would take, and I'm going to do this shorthand notation. Because remember, we should put plus H2O, H3O plus acetate. That would be the better way to do it to identify the Bronsted-Lowry and the Bronsted base. That's better for that. For Ka and Kb problems, we're not going to put the water unless we have to. For this one, we don't, and it'll just make the math a little bit simpler. Again, the key is weak acid. So it is a true equilibrium, and we've used this one a ton. And I'm going to streamline this. Ka is this times this divided by that. And then we look up the Ka. That's the setup. That's the setup. You can probably finish it from here. Weak acid, this is a weak base, but I don't see any OHs in there. I don't see any OH, well, because this is a Bronsted base. So we have to consider the actual reaction with water. Where are we getting the OH minus? We're getting it from the reaction with water. So we actually do have to write it in here to show the chemistry. And keep in mind, remember we did this before, generically we called this B and this HB plus, well that's what's happening. So that's B, and that's HB plus, just so you see that. And water we ignore. Minus X, whoops, it's not 1, is it? It's 0.1. Starting to look familiar? So in this case, we're going to have KB, because it's a base, equals x squared over 0.10 minus x. Okay, now, can you handle it from here? What I'm going to do, I'm kind of going back and forth here a little bit. Okay, now we can go back and look at equilibrium problems. We want to solve for x here, and we want to solve for x here. I'm going to give you the KV. Did I? No. Sorry, that's what I get for doing two problems at once. Now, I'm not going to set up all the math here. I think you can handle it from here. Now, remember what we do in these cases. We have our 5% rule. Can we apply it? Well, we have to do it and see. So let's try the 5% rule here. Try it. So let's assume that this is approximately 0 compared to 1. It's not 0, we can't put that up there. And I think you can do this math, because we've done this before. We just bring this over here and take the square root, and we get x equals 4.2 times 10 to the minus third molar. Okay, well, how do we check the 5% rule? Well, remember how we do that? We take 4.2 times 10 to the minus third over the original concentration. By the way, that's the same as percent ionization. It's the amount of H plus that's produced divided by the original concentration times 100. And I'll let you do that. Check, it works. The 5% rule is perfectly fine. Double check that. If you're ever not sure, go ahead and solve the quadratic equation. It's no problem. And then you get x here is 4.2 times 10 to the minus third. Well, lo and behold, x is not just x. X is H plus. Okay. pH, therefore, is, well, 2.4. I'm really sketching this. I'm not showing you every single step here, because we've done this before. Set up the ice table, solve for x. Well, x is our H plus, and you get 2.4. Okay, well, the acetate is also 4.2 times 10 to the minus third, and the acetic acid is 1 minus this. So that's a problem we've done before. I think I can kind of leave that sit out there. So, well, okay, I'll just do it for argument's sake here, because we need, so that's also the same thing. And then to get the acetic acid undissociated, which take 1 minus that, you should get around, not much less than 1.99 molar, because it's weak, it just didn't change very much. So that's a classic kind of problem I expect you to be able to do. Given an initial concentration, do an ice analysis, get the pH, and sure, I could ask you to do all the other stuff. pOH and percent ionization would be this. Okay, the other one I did on purpose This one I set up on purpose. The 5% rule does not work on this one. But I'm going to let you figure that out. So just do it. Assume that this is small, solve for, this is 0.1 this time, so 0.1, bring it over here, take the square root. Now this actually makes a little bit of sense. So I want you to do the math. You should get, I came up with the percent ionization. Well, checking the 5% rule, I came up with 6.6%. That's what I got, 6.6% when you assume that this is small and just bring this over here and take the square root. So just do that math and it does not work. So, I'm sorry, I kind of lost my train of thought there. Why doesn't it work? Well, two reasons. This K is bigger than this K. So the equilibrium is farther to the right, which means X is going to be a little bit bigger than over there. So it's farther to the right here. It's a stronger base than this is a strong acid. The other thing is, concentration is really, really small. This is 0.1. This is 1. This is 10 times smaller. So the assumption that X is small doesn't really make sense here, which kind of makes sense, sort of. So you have to go through and do this quadratic equation, which I think you can do that one. I don't think I need to show all that. So we would bring this over here and set it up in a quadratic equation. I'm just going to show you the final answer. Now, if you need help with those, just make sure that you see me or you bang these out. I'm just going to give you the answer. So you do the quadratic equation, and you come up with X equals 6.4 times 10 to the minus 3 molar. Well, okay, how does this answer the question? Well, it's the same as before. So this would be the concentration of the cation, would also be the concentration of the OH minus, which we want, and then we take 0.1 minus this. I'm not going to write all that out. So that's how you would find those. And then the POH would be the minus log of this. So you get the POH of 2.2, which means you have a pH of 11.8. That is a classic type of problem I would expect you to be able to do. I may end there. I'm going to show you one other type of problem that's going the reverse direction, and that's where we're going to stop with calculations with this section, which is perfectly fine. So this is calculation number 1 is given the Ka, do all of this. The second type of calculation is the reverse. If you're given the pH or the POH, how do you actually calculate the Ka or Kb? It's not something I want to dwell on, but it's kind of nice to see the logic because it fits in, and it's something you're going to use in your lab, whether you have 126 lab or you're a major that has lab with Dr. Richardson. So, okay, so I'll give you a chance to kind of get caught up there, and I'm just going to show you a couple of examples of this. Yeah, these actually these ones are pretty easy compared to this. And I'm going to do 2 examples side by side. So just give me a second here. And we're going to change this up. Two examples side by side. So in this case, we are given an initial concentration, like we always are, and a pH or a POH, because one tells you the other. This is not a very typical type of problem. What most books do is just kind of round out the math, and this is where we'll round out chapter 14, I think. And, oh yeah, and I kind of cheat. The examples that I use are right from your book. One of them is an exact book problem, and the other one is a check your learning problem from section 14.3, I guess. Fine. All right. Works for me. Example 1 and example 2, and there's one last piece of the puzzle I'll throw in at the end. So this is kind of a long video, sorry. So example 1, this one we have to be careful. HNO3, nitric acid, is a strong acid. HNO2, which is called nitrous acid, is a weak acid. Just so you know, that's the stuff. And you're given a pH of 2.34, so you can do all the other stuff. But you're going to need that skill. That if we want the H plus concentration, which is equilibrium concentration, we're going to need that. It's 10 to the minus 2.34. The other example is, again, it's a check your learning problem, is you have some ammonia. Probably recognize that as a base at this point. In this case, you use a pretty good pH meter. It goes out to 3 decimal places. Those are expensive pH meters, but we have them. Okay, so we have a weak acid and a weak base. It's good to recognize that. So we're going to calculate a Ka here and a Kb here. How do you know that? Well, the pH is less than 7, so this is acidic. The pH is greater than 7. This is a base. So you got to take your cues from what is it you're dealing with. So for this equilibrium, we're going to write HNO2 in equilibrium with the shorthand version. Okay, this is a base, so molecule B plus water in equilibrium with ammonium. Fine. Okay, it's sort of an ice problem. It's not as interesting of an ice problem. It's kind of a reverse. This is something you'll see again in the lab. And what are we trying to calculate in this problem? We're trying to calculate Ka. So we're trying to calculate this times this divided by this. We want numbers there. We want to calculate a Kb. We want this times this divided by that because we ignore the water. So we need numbers for all of those. But we don't have any X's or, so what do you do? All right, well, this is how you do it. It's almost a reverse ice table. You know that the initial concentration starts out at 0.0516. 0, 0. Well, X's aren't going to do anything for us. We can't have X's and solve for an X that we don't know, Ka or Kb. That doesn't help us. So the initial concentration here, 0.950. 0, 0, it's the same math, by the way. So how are we going to do this? Well, here's how you do it. We jump to the end of the table, and then we go back. What? We actually jump down here, and then go back. It's kind of odd. Well, if you know the pH is 2.34, we know that the equilibrium is skipping this one. We know that the equilibrium concentration is 10 to the minus 2.34. We know that. Every time we form an H plus, we form an NO2 minus. It's a 1-to-1 ratio. double check all of this. If you do that math, this is 4.57 times 10 to the minus third. So is this. Okay, well, that's how much it had to change. That's our x value. So this had to go down, up by that amount. This had to go up by that amount. Well, this has to go down by that amount. So just take 0.0516 minus this, and you come up with, see that? The pH indirectly tells you what your x is. That's what it does, because it's an equilibrium measurement. And because it's 1 to 1, it's pretty straightforward. So just take 10 to the minus pH, get those are your x's, and then reduce the initial by that amount. So we've got now Ka, because it's an acid, is going to be H plus times NO2 divided by HNO2. So it's going to be 4.57 times 10 to the minus third, and that's times itself. So let's just be sneaky and do that. Divided by 0.0470 molar. Ka in this case is going to be equal to 4.4 times 10 to the minus 4. And the units there are going to be molarity, but it doesn't really matter. The Ka. So that's the Ka for this one. See how that works? You just kind of reverse engineer it. Take your pH and reverse engineer it. This one is very similar, except we're given a pH, so we're going to want to find the pOH and do the exact same thing with that one little twist. So don't write 10 to the minus pH here, because this is a base. So I'm just going to set this one up and write it out for you. Cool. So just don't forget that little thing there. So if it's a base, we want the pOH in this case. So 14 minus 11.612. Enter 2.388. So the pOH is 2.388. Unitless as always. And just go ahead and set up the math. You can do this one. I'm just going to set it up and give you the answer. So the equilibrium concentration of OH minus is going to be 10 to the minus 2.388. So is this 10 to the minus 2.388. And then this has to go up by that amount. It has to go up by that amount. This is you can fill this one in yourselves. This has to go down by 10 to the minus 2.388. You just do all of that math. I'll just give you this one. When you do that, you get 4.093 times 10 to the minus third for all these values. And you end up getting for the equilibrium concentration 0.946. It doesn't go down that much. So in this case, Kb equals 4.093 times 10 to the minus third squared all over 0.946. .77 times 10 to the minus 5. Again, this is something you're going to use a little bit in lab. Not because you can go in the lab and measure a pH and calculate a Ka. Because that makes sense. pH probes are easy, although we're not going to get a chance to use one. All right. I'm going to show you one last thing. And not make a big deal out of it. It's the last calculation, so sorry this video is getting really, really long. And And it's actually a pretty simple equation. It's actually how to relate a Ka and a Kb. How can you get one from the other? This is very simple compared to what we've done before. So this is the last type of calculation. Because as you recall, sometimes things act as acids, sometimes they act as bases, and you want to be able to interconvert them. It's a very simple equation. In fact, I'm going to give you the answer now. If you take the Ka of a weak acid, and you multiply it by the Kb of its conjugate base, going in the reverse direction, this is a conjugate acid-base pair, take the Ka and multiply it by the Kb, that equals the Kw. So you can convert one to the other. That's the final answer. Ka times Kb for a specific chemical, not just generically. So that's the final answer. I'm going to show you where this comes from. Let's just stick with acetic acid. Now I'm reverting back here. I am reverting back to Bronsted-Lowry. So we have Bronsted acid, Bronsted base, showing it more explicitly. Fine. Well, okay. So this is an acid. This is its conjugate base. Definitions from before. What does that mean? We didn't go into this too carefully. If this is a conjugate base, this actually has some basic properties to it. So the acetate ion is the conjugate base of acetic acid. What? Okay. What is that? What that means is that this ion can actually react with water in a separate equilibrium as a base. I don't want to get too hung up on this. So this equilibrium is also taking place, where the acetate is acting as a Bronsted base. That's an extension of conjugate acid-base pairs. I don't want you to get too hung up on this. So this is an acidic equilibrium. This is a basic equilibrium. So I'm just going to show you this. Ka times Kb. I think you see where this is going. Let's just put in the symbols. So Ka is this. That's Ka times Kb. And we don't write the water, remember that? And if I did this right, well, that cancels, and that cancels. Okay, that's not that interesting, but it's another useful tool to have. Is if you know the Ka of acetic acid, you automatically can calculate the Kb of the acetate ion. That's kind of the point that why we do this. Is sometimes when you're given tables, they won't give you all the Kb's. In fact, a lot of tables, they just give you the Ka's and expect that you'll be able to calculate the Kb on your own if you need it. So the Ka of acetic acid is one thing, the Kb is simply solving the equation. Let me show you one example. One example of this, and I think this is officially where we will end up. Oh, I didn't actually finish the examples for you, so the Kb for acetate would be 1.0 times 10 to the negative 14th divided by the Ka of acetic acid, which we wrote down before. Or you look it up in a book. It's pretty simple. Just take the K, just solve the equation. So it's Kw divided by Ka. So that was example one. If you have your tables that you're using in front of you, the Ka tables, I don't think you're going to find the ammonium ion there anywhere, or ammonium chloride or ammonium iodide or anything involving the ammonium ion. Go ahead and check. I don't think you're going to find that. What you will find, however, is the Kb for ammonia. Because ammonia is a weak base. And I think we have it, incidentally, it has the same value. That's just a coincidence. So, if you want to know the Ka of ammonium, and you're given the Kb for ammonia, well, that's pretty straightforward. Ka times Kb equals Kw. And we just solve the equation. And so Ka would be 1 times 10 to the minus 14th. All over Kb. And actually, that's kind of interesting. We get the same answer, don't we? All right, so that'll be the final, I believe, acid-base calculation that we will do. So relating a Ka and a Kb, so the Ka and Kb of two conjugate acid-base pairs. And that's a nice way to wrap up chapter 14. And if we do anything more with that, I'll add it on later, but I think that's good enough for now. Okay, take care, folks.